Okay, in this video we're going to take a look at how we would integrate if we're in spherical coordinates. Okay, so we know that anytime we're integrating, we're going through this four-step process where we would chop things into little pieces, approximate the, in this case, signed hypervolume over each piece, add them all up and take a limit. Okay, the question is, what are we chopping them into? And for spherical coordinates, we would be chopping things up into what are called spherical wedges. Now with rectangular coordinates, we chopped things into a rectangular box that was bounded on all six sides by six planes, which are just constant surfaces in rectangular coordinates. In cylindrical coordinates, we chopped into cylindrical wedges that was bounded by six constant surfaces, two of which were going to be cylinders, two of which were half planes, and two of which were actual planes. Here I'm going to have six constant surfaces, so we'll have rho equals rho 1 and rho equals rho 2. So we're going to have two spheres. So we're looking at the region in between two spheres. And then we'll have theta equals theta 1 and theta equals theta 2. And so we'll have two half planes. So our region is also going to be in between two half planes. And then we'll have phi equals phi 1 and phi equals phi 2. So we'll have two half cones, including the possibility that one or more of those is a degenerate cone, either just a single ray or the entire xy plane. So what we need to do is see if we can't figure out what the volume of a spherical wedge is, because that's going to be the delta V that when we take the limit becomes the dV. So what I'm going to do is I'm going to draw a picture of the cross section that I would see in one of these theta half planes. So here's the z axis. This would be the xy plane. We're imagining that it just extends on out like so. Now I usually draw it so that it looks like we're talking about the right half of the yz plane, but I'm not assuming that we have that. I'm just taking whatever half plane I have and rotating it so that it fits nicely on my whiteboard. Okay. So just in there, if I had two half cones, so this would be phi equals phi 1 and phi equals phi 2, these rays are the intersection of a half cone with my half plane. If I look at the intersection of my spheres with the half plane, the intersection of a sphere with a half plane is just going to be a semicircle like so. So this is the cross section of my spherical wedge in just a single theta half plane. So this is taking into account 5 of the 6 boundaries that we'll have. And what we're going to do then is we're going to basically take this half plane and rotate it so that it's not quite the same as extruding this shape. It's rotating that shape just a little bit as we allow theta to change. Now you'll notice that looks essentially like a polar rectangle, and it essentially is, because it's determined by two rays and two circles. It's just those circles and those rays are intersections of spheres and cones with our half plane. Okay. All right. Now, I'm going to start by approximating the area of this. Just the area that we have here that we're then going to rotate as we allow theta to change. So if I take a look at this thing right here, this side is actually just delta rho. That's literally the difference between the bigger rho value and the smaller rho value. For this side here, I want to notice that this angle, if I were to extend these phi rays to the origin, this angle right here would be delta phi. That's the difference between phi 1 and phi 2. Now, keeping in mind that delta rho is going to be small, because we're going to chop things up into small pieces, the length of this side and the length of this side are going to be very, very similar. And they're both just arc lengths on a circle. They're the arc length that corresponds to this angle, delta phi. Okay. Now, if we think about calculating arc length, if I had a circle of radius r, and I had some angle, let's just call it alpha, okay, and I wanted to calculate the arc length that's swept out, we usually use s for arc length, s would just be r times alpha. It's just the angle times the radius. Why is that? Well, if we think about what the angle in radians means, the definition of radian measure is that it's that ratio. It's the ratio of the signed arc length that gets swept out by the angle and the radius of the circle. Okay. So I can approximate these sides here, which are curved, by saying that's going to be about just that angle, delta phi, times the radius. So I'm just going to pick a representative radius, which I'll call rho star, and say that's times delta phi. Okay. So I could approximate the area that I have right here as being approximately rho star times delta phi times delta rho. Now that's an approximation because this isn't actually a perfect rectangle, but it's close. So I'm just approximating, saying that's about what it would be. This is not a formal proof. This is just an informal explanation of our formula. Okay. So now I need to calculate the change in theta. So I need to account for the fact that we're going to rotate this shape forward. So forward or backward, I'm going to do it forward because that's easier to draw. Okay. So I've got this sort of a shape, and I'm going to allow theta to vary. So I'm sort of rotating this to change my theta, and so I'm getting something that looks something like this. That's sort of the shape of one of these spherical wedges that we would have. Now what I need to do is I need to approximate now. I've approximated this side and this side. I need to approximate one of these sides that corresponds to the rotation of the theta. Now to do that, I'm going to just draw in my axes here, and I'm going to try to project this down onto the xy plane. Obviously, I've chosen to draw this in octant 1. It doesn't have to be in octant 1, but it's easier to draw there. Now, if I project this down onto the xy plane, I'm going to have a curve that looks something like so, where this would correspond to the theta value that I have that was giving me the original half plane, and this would correspond to the theta value for the other half plane. So that this angle right here is delta theta. Okay. So the change in theta is between those half planes, but when I project it down onto the xy plane, essentially this is the intersection of one half plane with the xy plane, and this is the intersection of the other. Then this little curved piece is again actually just a section of a circle. It would be a circle of radius r, where r would be the cylindrical coordinate that I would have coming out to the points that I projected down. Okay, so I know what r is in spherical coordinates because I've got this lovely triangle, ZR rho phi. I know that sine of phi is r over rho, so r is basically rho sine phi. So I can approximate that this length is about rho star sine phi star times delta theta. That's my R value times the change in theta for some representative rho and phi value. So, although this isn't a rectangular box, if I borrow the formula that it's length times width times height, or this dimension times that dimension times that dimension, I can say, okay, I can approximate the volume of this here. I can say that delta V is approximately the area of what I had in a single theta half plane times the distance that I have when I rotate things forward. But that's going to give me rho star squared times sine phi star delta rho delta phi delta theta. Okay. So I get one factor of rho, my representative rho value here. I get a second factor here in addition to a sine of phi star. Okay. So that's an approximation of my delta V. Okay. So, turns out that's the right approximation. Now this isn't a formal proof. This is just an informal explanation of why this works. But then when we integrate, it's going to turn out that our dV is going to be rho squared sine phi d rho d phi d theta. Okay. And I'm almost always going to integrate in this order, d rho, d phi, d theta. Not absolutely necessary, but I think that's going to be the simplest as far as setting up our limits of integration. So I'm just going to get in the habit of writing it like that. And in our next video, we'll take a look at actually doing an integral.